定理。20世纪初期，菲尔兹在证明黎曼罗赫定理的同时，致力于全球数学交流。1941年，海蒂拉玛和安泰尔发明的调频技术落地于无线通信系统。1965年，戈登摩尔总结实践经验，提出了一直被追赶的摩尔定律。2000年，高锟推动建成世界上第一条1公里长的光纤网络。1986年，杰弗里·辛顿将反向传播技术应用于深度学习。科学研究和技术发展就是这样一步步向前迈进。链接实践和整合资源，积极探索和开拓创新，讨论碰撞和相互激发，人才发展和融合生态。查斯乌科技网站汇聚全球高价值科技。
Good evening, everyone. We are very delighted to have you all join us today for the first session of our new masterclass series, The Evolution of Physical Layer Communication Waveform, presented by Huang Danian Charles Park. And this series is dedicated to explore the systematic shift in waveform design, a cornerstone for 6G technologies, aiming for high mobility, low latency, and integrated sensing and communication. Over the coming weeks, leading scholars around the world will guide us from the fundamental series to future applications. Tonight, we are honored to launch this journey with a comprehensive tutorial, and we are joined by Dr. Shuangyang Li, from Technical University of Berlin, and a distinguished researcher in signal processing and communication. His talk is titled A Tutorial View on Physical Layer Waveforms. This is a brief introduction of abstract of his talk. And let me briefly introduce Professor Shuangyang Li. Shuangyang Li received the bachelor, master, and PhD degrees from Xidian universities, and also a PhD degree from the University of New South Wales. I'm also coming from UNSW. He is currently a junior research group leader at Technical University of Berlin, TU Berlin, where he is a principal investigator of an ERC starting grant project. Very impressive. Previously, he was a Marie Curie research fellow at TU Berlin and a research assistant at the University of Western Australia. So he also received many best paper awards, and now he is served as the editor of TCOM. His research interests include signal processing, channel coding, applied information theory for communication systems, with a focus on waveform design. And also, I forgot to introduce myself. I'm Zhiqiang from Xi'an Jiaotong University. So without further delay, let's give a very warm welcome to Dr. Shuangyang Li for his excellent talk.
Thank you, Zhiqiang, and thanks for the nice introduction. And it's a great pleasure for me to be here. Maybe I should start sharing. Yeah. Okay. Oh, it's here. Can you see my slides?
Yes, I can.
Yeah, I'll just full screen. Is it okay now?
Yeah.
Yeah. Okay. Thank you very much. And as I mentioned, thanks to Zhiqiang for this very warm welcome, and it's a real pleasure for me to be here to kick off on our series of talks on physical layer waveforms. I'm Shan Li from Technical University of Berlin, and today I'm going to give a kind of introductory view on waveforms in general. And I hope this can motivate people's interest, and especially going to follow on the course in the next coming talks. So the outline of this talk is that I will first go with some of the backgrounds on wireless communications in cellular networks, and then I'm going to talk about various channels and why it's difficult to do reliable communications over such channels, and also the fundamentals on classic communication waveforms, followed by new perspectives on advanced waveforms. After that, I'm going to talk about briefly, of course, waveform designs for integrated sensing and communications, and finally, a quick research direction for future research. I'm going to start with the background. As we have seen over the past few years, the wireless communication, especially for the cellular networks, there have been a noticeable evolution from first 1G to currently 5G and go beyond 6G. We have seen that waveforms are going to play an important role in each era of generation. For example, we start from the analog FDMA and then turns to TDMA, CDMA, and now it's currently using OFDMA and plus some of the superposition code decays NOMA. However, we can see that waveform is one of the key cornerstone for reliable communications, and nowadays, because we are going to face more challenging scenarios, for example, we need to accommodate more advanced applications, and these all challenging factors pushing us towards to investigate more advanced waveforms. Particularly, I want to highlight that the future wireless waveforms are required to support higher data rate and need to have a strong capability to combat interference in order to serve multiple users, and also need to be able to exploit channel dynamics, especially in some challenging conditions such as high mobility. And also, it needs to be accommodated to more emerging various technologies such as radar sensing, such as edge computing, and even artificial intelligence. But clearly, the trend is that our carrier frequency for wireless communication is going higher. We currently from sub-6G to terahertz or even visible light communications, and currently the 6G going to use FR3, which is also a higher frequency compared to the sub-6. We are going to see more complexity in the channel. We need to be aware of the distortions and the significant fluctuations in such as non-terahertz networks, UAVs, and high Doppler cases. And we also need to accommodate variation, a lot of different tasks, such as the UAV communication or underwater communications. And the main challenges for these cases is that the communication and the rate, they are always a trade-off. But of course, under challenging channel conditions, what will be the trade-off? What should we design our waveforms to support higher rate and more reliability? And also, we need to adapt to more emerging applications such as sensing and other type of communication as mentioned. And also, we need to change our view from combating the channel to exploiting the channel. That means we do not need to see channel as a drawback, especially when it's fluctuating. We need to somehow use a systematic way to exploit the dynamics of the wireless channel in order to improve the performance. Now I'm going to give a quick revisit on the various channels. I'm going to do a very quick one here because this is, of course, people in communication engineering are already aware of. So we are familiar with this static multipath channel. For example, if we have a base station which is going to transmit a signal through multiple paths, for example, the signal going through this building and reflected to the receiver, and this can also be bounced by a tree. So basically, the receiver receives a signal from 3 different paths, and this is what we call the multipath channel. In multipath channels, different paths, they have different lengths. That means the delay of your signal received by the receiver may be different. And this gives us the frequency selectivity, and this is caused by the multipath channel. Alternatively, we also have this non-static single path channel. A good example may be a UAV, which is flying in the sky, And in this case, we are having a very good directional channel, maybe just one path. But because the UAV is moving, that means there is a velocity against the transmitter and the receiver that gives rise to a so-called Doppler shift. And this Doppler shift can cause signal shifts in the frequency domain, which is also be characterized by the Doppler spread in this condition. And nowadays, it's more challenging that we need to compare this. We need to consider so-called doubly selective channel, which means that we have both delay spread and also Doppler spread. A good example may be the communication over a highway. That when, for example, this purple car wants to transmit a signal to this blue car here, and this transmission is going to be reflected by several cars here because the cars are moving and there are multiple cars. Therefore, you are suffered by both delay and Doppler. And this is actually going to be difficult to deal with because conventionally, when we have this frequency selective channel, we know that the signals can be reflecting in the frequency domain. Therefore, we can use OFDM by truncating the whole bandwidth into several subcarriers to improve the performance. And for the frequency dispersive channels, that means time selective channels, we can do TDMA. For example, we transmit signals in different time slots. However, if we are going to deal with the doubly selective channel, that means we need to have something that to be transmitted in both time and frequency in order to improve the performance. And this is proven to be difficult. Let me be a little bit specific on how this deal with how the channel characteristics in this case and how this is difficult. For example, we consider first a static channel, as I mentioned here. We can see that the signals going through two paths, and each path has a different time delay, and therefore what you receive is actually two replicas of your transmitted signal at different time offsets. For example, here we have tau 0 equals to 2 and tau 1 equals to 3, and these are separated in time. And in the doubly selective channel, on the other hand, we have another dimension which is actually corresponding to the Doppler. That means what we receive is actually delayed and also frequency shifted. And that means we can separate the paths from more than one dimensions. That actually gave us an advantage in characterizing the different paths. And this is precisely one of the motivations for the new designs of advanced waveforms. I'm going to give a little bit of general overview on the channels in different domains. I have mentioned that if your channel is delayed in time or shifted in frequency, you can represent your channel responses in time or frequency. And this is actually aligns with this picture here. Because for example, if your time can be represented in the so-called time delay domain. Basically, you have an impulse response in time, and this is also corresponding to at each time slot, you have a delay offset. However, if you do a Fourier transform along the delay dimension, along the delay dimension, you ended up in the so-called time frequency domain, where you can see that your channel responses have different values at different time slots and also frequency subbands. And this is actually, you can see they have different fluctuation, therefore it can be troublesome for communication. Alternatively, if you do a two-dimensional Fourier transform from the time frequency domain, or equivalently one-dimensional Fourier transform from the time delay domain, you have obtained the so-called delay Doppler domain channel. Here is a really different because after the Fourier transform, you can see the paths are represented by several potentially distinct responses here. And these are, for example, if you have P paths, ideally you can only receive P spikes in the delay Doppler domain. A very interesting aspect I want to highlight here is the so-called coherence region and correspondingly the stationarity region. The coherence region is a type of is a definition on the time frequency which says that the channel dynamics, channel coefficients within this area are roughly constant. However, in the delay Doppler domain, we have no such definition or such region. Instead, we have the so-called stationarity region. This region is characterizing an entire environment such that within this environment, your delay and Doppler remains constant. Therefore, this is more related to a geometrical interpretation of your channel. For example, if I'm talking currently in a room, there's nobody moving or nothing changed, my delay Doppler domain channel remain the same. However, this does not hold in the time frequency domain because we have a coherence region. That means if, for example, if I'm talking with in this room, the channel responses in the time frequency domain can be changed. But however, there exists a so-called coherence region, the exact channel coefficient may be unchanged. Okay, a quick summary comparing the time frequency domain and the delay Doppler domain channel. That in the time frequency domain, the channel responses are dense because it's everywhere, and it can be difficult to be exploited to estimate the time varying nature of the channel. However, in the delay Doppler domain, because of this stationarity region, the channel responses can be compact and also stable, and this allows potentially accurate and low overhead channel estimation. However, I want to be fair in the sense that there's no optimal solution for everything. For example, the delay Doppler domain channel can be beneficial in some tasks, but the time frequency domain can also be advantageous, especially when you are trying to have some low complexity transceiver designs for communication. And therefore, a good engineering problem is actually how to balance these various domains and how to exploit these dynamics based on the particular requirements on your task. Okay, this is a quick summary on the delay Doppler domain channel features that we have potentially separability, meaning that, for example, in this picture here, which I copied from this book, in this picture here, you can see that if we only look at the signal, the channel dynamics from the frequency domain, we can see at most 3 different spikes. However, if we look at the signal responses in the time domain, we may have 4. But actually, there are actually 5 different reflectors within this area. The only way to explore both of them is that you need to look at your channel from both time and frequency, and that corresponds to the delay Doppler channel representation. And the separability means that even though some of the reflectivities are having the same frequency or time, they can be fully separate if you look at a 2-dimensional case responses. And this is one of the good things for delay Doppler domain channels. Another thing is that it is stable. As I have mentioned, it corresponds to an environment, particularly on the geometry of your transmission environment. That means only the burst changes in the propagation paths can change the delay Doppler responses. Therefore, it lasts for a larger time. And there is also compactness because the maximum delay and Doppler can be known before your transmission. For example, if you are in a cellular communication case, your cell has a certain size, and therefore it allows you to calculate the maximum delay within this cell. And this is somehow useful because the delay Doppler domain channel can be compact, and therefore you have some priori information for your channel estimation. And finally, this delay Doppler domain responses can be potentially sparse. That means only a few of the propagation paths are available or visible in the delay Doppler domain. That corresponds to some large scatterers. And this can be interesting and also useful for us to exploit, especially if you want some low complexity transceivers. Okay, now I have been talking about the channel part. I'm going now to the fundamentals of some classic communication waveforms. For example, the classic communication waveforms, I want to give a very elementary introduction to this, is that we can see as this waveform as a continuous time signal that conveys a certain amount of information. Basically, in this case, we have Sn, which is the information symbols for transmission, and we have this PNT, which is so-called basis function to carry this information. Because the information symbol can be discrete, but we only need to transmit something in continuous form. Therefore, each symbol need to be accommodated by a continuous pulse, and together, if we sum them up, that is the continuous time communication waveform for the transmission. And normally and typically in practical systems, they are linear combinations of your information symbols and the basis functions. However, the key point here is that directly designing ST in this continuous form can be difficult because of the continuous time nature and also the hardware limitations. Therefore, people typically separate these tasks into two. For example, we need to design modulation, which is basically a discrete transform on S, and combined with a post shaping, which is changing, which is a mapping that corresponds to, that maps your discrete symbols to a continuous waveform. And these are the two important tasks for waveform designs. I'm going to give some good examples on the typical communication waveforms. And of course, the most simple one and the most straightforward one is the single carrier waveform. And in single carrier waveforms, normally we transmit signals in this form. We have Sn and we have Pt. And for each symbol Sn, we have a time-shifted version of Pt as the basis function to carry this information. And Pt here is representing the so-called prototype pose. And this whole thing can be implemented very easily using a convolutional filter by just convolve your transmitted signals with your continuous pose here. And here, T represents the symbol time, which is roughly the duration of your corresponding to this symbol. An important concept here is the so-called Nyquist pose, or more precisely, root Nyquist pose. For Nyquist poses, we need to satisfy a certain type of orthogonality. That means for this pose, if it's shifted by integer multiples of t, we have a delta function. That means there will be no interference for different, as long as this signal is moved in terms of multiple times of t. And equivalently, this can be represented in the frequency domain, ended up in this equation here. This is actually the folded spectrum for Nyquist poses. I'm sure that people are familiar with this concept, which is, of course, in the textbook and known as the Nyquist no ISI theorem. And if we consider such a type of a waveform going into a doubly selective channel given by this delay Doppler domain responses, we can see the received signal is purely the attenuated, time-shifted, frequency-shifted signal of what we transmitted, plus a noise. And after match filtering with respect to the pose we used here, we have this so-called intersymbol interference channel in general for this type of transmission. And here, the ISI intersymbol interference coefficients can be calculated based on the channel dynamics and also the ambiguity function of your pose, Pt. And the ambiguity function is actually a well-defined concept with respect to the different time shifts and frequency shifts. And together, the ambiguity function gives you an overview on how sensitive of your pose with respect to time shift and frequency shift. And particularly, if we are in the regime of static channel, meaning that there is no Doppler shifts, this nu p equals to 0, we can see that this two-dimensional coefficient n prime n index is only corresponding to the offset between these two integers. That means our channel is time invariant. Let me be more specific in terms of the matrix form. If we put up everything in a matrix form, we can see that the received signal is purely a linear system with respect to what you transmitted plus a noise. And in time invariant channels, this G corresponds to a banded Topli's matrix, which means that for each rows, the coefficients are the same. Of course, I mean, I'm talking about this part here, because you are in Topli's matrices, you are simply repeat and shift your coefficients per row. And this is because we do not have Doppler. Therefore, there's no changing in time. However, if you are in the time varying channel, you are suffering from this time variation. Therefore, these coefficients are no longer the same. In fact, you can see that these variations changes with different rows because these index are changing. I want to also emphasize on the fact L here, which represents the most significant numbers of channel types. In most of the various channels, especially when you are using when you are considering the impact of post shaping, this L can be large. But however, some of the channel types are approximately zero because of the bandwidth and the symbol duration of your transmission. And in this case, especially given the fact that your channel types is typically smaller than the number of symbols you transmitted, you have this banded top-leaf structure and also this banded time-varying matrix. Another important type of waveform is the so-called multi-carrier waveform, and a good example is OFDM, of course. I'm going to briefly introduce this concept. Here, the multi-carrier waveforms actually takes the following form. We can see that for each information symbol xmn, meaning the information symbol on the mth subcarrier, nth time slot, is actually accommodated by a basis function, which is the time shifted and frequency shifted version of your prototype pulse. Here you can see that these two things together gives you a two-dimensional basis function, and therefore we need to have a two-dimensional summation to obtain the time domain transmitted signal. An important concept again is that t means the symbol time. That means your symbol is approximately transmitted in time for that long. And correspondingly, you have a subcarrier spacing concept, which means that your symbol corresponding to such amount of bandwidth for transmission. In most of the communication systems, we are considering so-called critical sampling. In critical sampling, your delta f, which is the subcarrier spacing, is the inverse of your symbol time. But it is important to know that critical sampling is not the only case we are looking for. For example, this whole analysis on different type of sampling goes back to the important discovery from Gaba, where he talked about the expansion, he talked about the partition of a time frequency domain using different type of Gaussian pulses. And in the critical sampling, we have the samples in time and frequency corresponding, the product of them equals to 1. In the oversampling case, we can see the product of them are smaller than 1, meaning that there will be some redundancy in the time in the corresponding coefficients here. And we also have this undersampling case where the product of f and t is larger than 1. That means what you sampled, you obtained samples are no longer sufficient to describe this two-dimensional signal. And these whole things are actually corresponds closely to the frame theory, which is also a well-studied mathematical problem. And here in typical communications, we consider the critical sampling in this picture here. Again, I'm going to derive the input-output relation with multi-carrier waveforms. For example, we consider the same delay Doppler domain channel given by this. We transmit this signal towards this this channel, and then we do a two-dimensional match filtering where we take the convolution with respect to the basis function here. After that, we can have a symbol-wise input-output relation given in this matrix here. And apparently, because we are in the regime of Doppler selectivity, therefore we may suffer from some interference from the adjacent symbols in different subcarriers, different time slots. And in certain types, in certain pulses, we can further simplify this equation. For example, when we are using the ideal pulse, which means that the ambiguity function with respect to different time of t and different with different tau and different nu delay and Doppler shifts, they are relatively small and approximately delta functions. That means if you are if this type of ideal pulse is in place, we are having a symbol-wise input-output relation that is simplifies to I think there is a mistake. In this case, we do not have these double summations anymore. We are only corresponding to the corresponding m and n symbols here. However, it is important to know that such ideal pulses is not exist in practice due to the Heisenberg uncertainty principle, but we can approximate this by using Gaussian pulses as much as possible. A more practical form is the so-called is the rectangular pulses here. And of course, we need to consider the impact of a cyclic prefix and with CP addition and removal, and together with the rectangular pulse, we are having some mathematically concise representation for this H. For example, if we do the CP addition and removal together, this H equivalently becomes a block diagonal matrix, which corresponds to several smaller channel matrix H here. And if we consider so-called on-grid delay and Doppler coefficients here, we can further write this in this concise form, where there's a P represents how many passes we have in the channel, and this HP is the attenuation corresponding to that pass. We have this tau and the delta matrices given by corresponding to the forward cyclic shift matrix and also the phase rotation matrix, and these are also corresponding, also related to how much, what is the exact delay and the delay index LP, and also the Doppler index KP here. And here F is the Fourier transform matrix, because in OFDM or in multi-carrier signaling, we are interested in the frequency domain channel. Sorry, I think if we are considering on-grid delay but off-grid Doppler, this effective channel need to be changed a little bit, because the Doppler are fractional in the sense. Therefore, we are having some additional term here, and the overall input-output relation still given by this H matrix. Okay, I have quickly go through the introductory in the introduction of the single carrier waveforms and the multi-carriers, and now I want to give some quick examination on the advanced waveforms. Particularly, I'm going to focusing on two types of waveforms in general. The first one is called propagation-centric waveform that aims to align your signaling with the channel dynamics as much as possible. And a good example for this is the so-called OTFS, orthogonal time frequency space. And I'm borrowing this picture from Zhiqiang's work. And the idea is that we can do conventional coding, interleaving, modulation, and also the pilot symbols as what we did before. But we need to consider a two-dimensional orthogonal precoding before we transmit that into the time frequency domain using legacy multi-carrier waveform modulators. And in this case, we can see that the delay and Doppler domain symbols are the information symbols are carried by different type of waveforms in different domains. For example, I have the delay Doppler domain symbols as a delta function, which is a discrete symbol. And then in the time frequency domain, this corresponds to a continuous waveform here. And in the time domain, we have another representation for the same signal. And after passing through the channel, we can do the similar things we can do the corresponding demodulation at the receiver side, and then doing the decoding and the demultiplexing. The idea, as I mentioned, is that we need to do a two-dimensional orthogonal precoding such that the signal we transmitted is aligned with the channel dynamics perfectly. I'm going to explain this in the following slides as well. An important concept is that because we are doing domain transformation, it is important for us to understand how the grid is changed with the domain transformation. For example, we are multiplexing our symbols in time frequency in the delay Doppler domain, and therefore, if we have n Doppler bins and m delay bins, after the two-dimensional Fourier transform, we obtain the time frequency domain equivalent representation, and here we have n time slots and m subcarriers, and that means we have this different representation of the same signal matrices, and these time slots corresponds to the OFDM symbol duration, and this delta F corresponding to the subcarrier spacing. And correspondingly, in the Doppler domain, we have the Doppler resolution, which is 1 over nt. That means we sample the signal. Which means we synthesize the signal with respect to the Doppler resolution given the total available time resources, and also we synthesize the delay, the symbol according to delay resolution as well, which is 1 over the bandwidth. Together, we can see that in the so-called delay Doppler domain, the symbols are multiplexed in a much finer grid. However, because of certain type of periodicity, this actually corresponds to the whole time frequency resources. I'm going to be more specific on the waveform transformations in different domains. For example, we start from delay Doppler domain. We have a time frequency domain signal, which is continuous, and then we have the so-called phase modulated pulse train in time domain, which is known as Poisson. And after going through the two after going through a two-pass delay Doppler domain channel, we can see in the time domain, it is also a superposition of two persons. And in the time frequency domain, we have a superposition of these two waveforms in a very difficult, in a way that is very difficult to deal with. However, in the delay Doppler domain, we can see what we have is, again, a simple shift of this signal here with replication. Sorry, this yellow thing is purely the replica of this blue symbol after going through this channel. This is precisely what I mean for propagation-centric. That means what we transmitted is aligned with the channel dynamics. If the channel has two passes, each symbol of our transmission is going to be represented by two dynamics, and everything is aligned with your time and frequency, with your channel. Therefore, we are able to use the minimum representation to describe this whole transmission. I'm going to give a little bit more examples on this. For example, if I place my symbols at different places in delay Doppler domain, we can see what we received is purely the replicas with respect to the channel coefficient, channel responses here. If you are transmitting multiple symbols here, what we have is the superposition, and still the replicas are following precisely the delay Doppler domain channel. And this is the so-called propagation-centric transmission. Another example is the so-called affine Fourier division multiplexing, AFDM, which is also have a good compatibility with the existing OFDM, for example. Different to OFDM, what we need is that two additional matrix calculations before and after IDFT. And together, the symbols are represented by this Fourier transform, affine Fourier transform with this two additional matrix form. And it turns out by doing so, and especially considering the maximum delay and Doppler, we can achieve a very good performance that precisely having the full diversity for the channel dynamics. And this is very good for reliable communications. Due to the time limitation, I cannot give more details on AFDM, but in our coming series, we have another professor going to talk about more on AFDM. Another emphasis I want to provide here is the so-called channel-agnostic waveform. And a typical example is the random multiplexing that is recently proposed by Professor Lei Liu. And in this channel-agnostic waveform, we do a so-called random precoding that is independent from the channel dynamics. For example, the key idea here is that we do not want to exploit the instantaneous channel structure. Instead, we want to statistically regularize your channel such that it has a very good or a very nice structure. And how to do that is actually going to use some of the powerful conclusions from random matrix theory. For example, we do a Haar matrix here, U. If it's a Haar, then we can show that it's a special type of a unitary matrix such that you can regularize your channel coefficients in an isotropical way. And this allows us to bring the powerful replica analysis into this theory in order to obtain, and this turns out to have very good communication performance. A key aspect here is that using this kind of regularization, we are able to describe this channel by a very simple scalar Gaussian channel with SNRs that is defined by the actual channel dynamics here. I'm going to be more specific on a typical example using the so-called faster than accurate signaling. So if we consider this random precoding together with FTN, we have the so-called random FTN signaling. Basically, what we transmitted is S, and then we have a random precoder. In this example, can be a Haar matrix, and then we have the obtained X, and then we do a post-shaping in a FTN way. I do not have the space to explain what FTN is, but it's a certain type of waveforms that transmit your signal faster than the Nyquist signaling, such that you are ended up with this ISI channel matrix. But it's intentionally, we are intentionally doing that because it can improve the performance. However, if you have this random precoder here, your effective channel is GU and plus ES, and ES of course is the symbol energy. And U here importantly is a Haar matrix, and we have effective this eta, which is a vector of colored noise. And we can do a little bit of derivations to give a mathematically concise improvement of relation by this AS plus N, where N is white noise, and A is actually the it still satisfies the it can be written here, and this lambda is actually the diagonal matrix, contains non-zero eigenvectors of your channel, and F is a Haar matrix. So this whole thing can be difficult, but I just want to highlight the key idea and the insights from here. As long as this A matrix satisfies this readily rotationally invariant ensured by this F Haar matrix, we can use the asymptotical, we can calculate the asymptotical normalized mutual information in this way. And here, this tau and tau t are particularly FTN symbols, FTN parameters that shows the, sorry, I think this equation mark is missing here. We have this tau and tau t are the specific FTN parameters that characterize the performance. But because we are having this spectral structures on A, we can calculate this in a more efficient way. For example, for example, we can calculate this by using the replica symmetry analysis. And this corresponds to 3 different terms. We have defined I1 corresponding to the scalar Gaussian channel, and we have I2 corresponding to the residue error, to the contributions of the residue error, and we have another offset term additionally. And this whole thing needs to satisfy the so-called fixed point equation. That means the derivation of I1 and derivation of I2 are equal eventually, and this is corresponding to the inverse of rho plus nu. And particularly if we are considering linear modulations and Gaussian channels, these 2 things can be written in these forms and can be calculated either numerically or in some cases analytically. And more importantly, for this fixed point equation, it can be solved by an iterative algorithm. And the iterative process actually corresponds to the state evolution of orthogonal AMP or vector AMP, which is our very powerful compressed sensing algorithms. And particularly, we can even prove that in the FTN case, when tau, which is the acceleration factor, when it's very small, that means we transmit our symbols much faster. And even with non-Gaussian constellations, we are able to achieve the total capacity with an assigned power spectral density. This is the very optimal solution for this type of transmission. I'm going to show these results here quickly to give you some of the flavors on this idea. For example, if we are using Nyquist signaling with QPSK, we are saturated at a certain SNR. Here, I'm considering spectral efficiency, and the unit will be normalized by the bandwidth we are using. Therefore, that's why we cannot have this QPSK equals to 2. But however, if we are using FTN faster than Nyquist, the capacity, the spectral efficiency is improved, and with a higher transmission rate, the spectral efficiency improves further. However, if we consider this random multiplexing in the place, we can even improve the performance more than FTN. And particularly, we can show that this is this going to have a very negligible gap with the optimal CPSD here. That is the optimal communication. It's the optimal capacity. Sorry, that's the capacity for this transmission, and it's the optimal communication scheme we can have. Okay, now I'm going to quickly going through the waveform designs for sensing, particularly in the regime of integrated sensing and communications. And I'm going to focus on the communication-centric design and also the joint design. In the communication-centric design, we are using standard communication signals. And of course, the good thing about this is that we do not sacrifice on the communication performance, but the sensing performance may be degraded. And in the joint design, we want to transmit our signals such that the communication part and the sensing part are already taken good care of. Of course, this is can achieve a scalable sensing communication trade-off, but it can be difficult to design. In communication-centric ISAC waveforms, most straightforward way is that we use our pilot to do sensing, while remaining using the random communication data for purely the communication performance. And in this case, I can show that using OTFS, especially with OTFS pilot, this can be very good for sensing. For example, in delay Doppler domain, we can place this spike pilot in the middle, and then we have a empty space, which is known as the guard space. Therefore, there will be no interference after the receiver, even though you have a time and frequency shift. And this spike, because it has such a strong power at the receiver side, it can be even though there are certain type of power attenuation, it's still noticeable by comparing with the other by comparing with the replicas from the data part. And this is a good way to do sensing because it's very simple and it's very straightforward. Another way to do communication-centric sensing is that we need to exploit the random communication symbols. And I'm not going to show too much details on this because we have a Professor Fan Liu going to give a very detailed talk on this particular aspect, but I just want to show how this can work and how this can be characterized in terms of the performance. A way to characterize the performance is the so-called periodic ambiguity function. And in this ambiguity function, we can have the expectation of the integrated side lobe levels for this periodic autocorrelation function. This autocorrelation function is a degraded ambiguity function that only focuses on the delay dimension here. And this whole thing can be written in a concise mathematical form. It turns out that the kurtosis of your communication constellation is going to play a very important role here. And this mu4 stands for the kurtosis. And we have Fn is the DFT matrix, and this U represents the unitary modulation basis for communication waveforms. A conclusion for this analysis is that in communication-centric ISAC waveforms, typically when we are using sub-Gaussian constellation, meaning that the mu4 is smaller than 2, OFDM is globally optimal for ranging, that means estimating delay, because it has a minimized side lobe level and also individual side lobe type. And this can be visualized by this factor here. For example, when we are considering 16 QAM, whose kurtosis is smaller than 2, and we can see that OFDM achieves a very low ambiguity function, side lobes, comparing to, for example, single carrier here, which is actually has a higher side lobe. And this also holds for 64 QAM. But interestingly, if we do a super Gaussian constellation, which means that the mu4 is larger than 2, the whole thing is reversed, and the OFDM actually gives you the worst performance. A good corollary for this conclusion is that the single carrier waveform is the only waveform that for Doppler estimation that achieves the lowest side lobe levels, because these two problems are dual problems. If we can show that multiplexing symbols in frequency domain is good for ranging, we can equivalently prove that multiplex symbols in time domain is good for Doppler estimation. And this is the insight here. Finally, I'm going to present a very quick and simple work for ISAC waveforms in the joint communication and sensing designs. In this case, we are going to use some neural networks to help our code word design because this problem is very difficult. This idea is that we have a transmission of S, which is a short sequence of bits. We want it to go through a neural network such that it maps to a complex sequence X for transmission. And then this complex sequence S is going through a communication channel HC and also a sensing channel HS. And at the receiver side, we are interested in the recovery of S for communication and the estimation of HS hat for sensing. And we have some detailed parameter here, but in general, I want to say that this whole thing is actually because of we are interested in the short code word length, we have to consider the non-coherent communication, which means we try to decode S without knowing explicitly on HC. And this is well motivated for short code word transmission because the affording pilot will cause a very large overhead in this case. So for the communication channel, it's a very simple channel. We consider a correlated channel with some rho C here. And this rho C corresponds to the correlation for different type of, for different symbols. And we have a sensing channel, which is also a diagonal channel on HS. And we can see, yeah, the covariance matrix of this HS is actually given by this. And this is the same for the communication channel, where the covariance matrix is given by RC. In the non-coherent decoding, in terms of a maximum likelihood, we can show that the Rx matrix is very important. And this is actually the covariance matrix with what you're transmitted plus your plus the impact of the channel. And in the special case where there's no correlation in the fading coefficients, meaning that rho C equals to 0, we have this corresponding to this part of the equation. And the key message, I don't want to bother you with the detailed mathematics here, but the key observation is that our communication information is encoded into the amplitude, but not the phase. Because our information symbols X here, and we can see that different phases of X does not correspond to any type of transmission. Particularly, we only care about the amplitude for this non-coherent transmission. As for sensing, because it's a diagonal matrix, we can do a very simple MMSE estimator. And we can see that the MSE equals to this equation, and according to the Jason's inequality, this MSE is lower bounded by this equation here. And again, we can see that the amplitude, the smallest amplitude, can give the best MSE, which is the sensing loss. And then we can see here there's that sensing MSE is potentially minimized by PSK signals, meaning that the symbols are having the constant envelope for transmission. But clearly, as I have mentioned, in communications, we prefer something with different amplitude, but in sensing, we prefer something with the same amplitude. Therefore, we can see there is a trade-off for communication and sensing. And to have a good solution for this, we borrowed the help from the neural network. And we have the communication loss, LC, which is a classic cross-entropy loss. And we have a sensing loss, which is MSE. And the loss function for training is basically the combination of these two with a tunable factor such that we can balance the importance of communications and sensing. It turns out that for sensing only transmission, all the symbols, all the code word we obtain is a constant, is around the constant envelope, which is aligns with our analysis. For communication only, we can see we tend to somehow give transmit some symbols centralized around the zeros, but sometimes we have some peaks at different times. And this is precisely the so-called on-off keying, where we send most of the symbols around 0, but all of a sudden we send a very strong power in order to have a good performance. And if we have a trade-off between the communication and the sensing, what we have is actually this flake-shaped constellation that is a combination of your PSK signal and also your on-off keying. An example can be seen here. For example, in this gamma equals to 0.8, we have most of the energy corresponding to the very central point. That means you are having a constant envelope, something very small here, but all of a sudden you somehow give a very strong spike at a certain time slots. And if your moves towards more around the communication, you have more. I'm not sure if you can see this clearly, but this is a very clear on-off keying case. But if you are changing towards more about the sensing perspective, you can see your constellation goes back to the constant envelope PSK signal. And our numerical results aligns with what we have described. In this short block length transmission, we can see by tuning the parameters here, we have a very noticeable trade-off for communication and sensing. And of course, this is with the help of neural network. And other than that, because in the short code length regime, it's very hard to design something theoretically. Okay, I have quickly going through some of the key aspects on waveform designs, particularly for next generation wireless networks. I'm going to give some quick summary on the future research directions. The first one is that we still need to focusing on high dynamical channel characteristics. For example, we need more measurements, especially for new applications. We also need to compare the similarities on the communication channels and the sensing channels. And the fundamental limits for communication over high dynamic channels are still unknown, even though we have some good understanding already, but there are still some lack in this direction. For example, we want to know the information theoretical understanding for this type of communication. We also want to analyze the attributable rate for non-coherent and non-coherent communications. Especially when we are considering MIMO transmissions, we want to know the capacity scaling and also the security and the privacy performances for this type of communications. For the waveform design, we are also in need of new directions. For example, we are still in lack of a good channel estimation and equalizations. We also need to have some robust schemes that is against the high channel dynamics. We need to ensure the backward compatibility with the legacy waveforms such as OFDM, and we also have some new latency designs for propagation-centric and channel-agnostic communications. We have other type of communications such as reliability with higher frequency and larger bandwidth, post-shaping, MIMO, multiple access, and also a neural network enhanced waveform designs. They are all very good research topics for future investigation. And as for the implementation, we still have a lack of low complexity implementations, and we also need to have a network architectures and transmission protocols need to be designed specifically tailored to the advanced waveforms. And for integrated sensing and communications, we need to have a thorough analysis on different waveforms, although we have some results yet, but still there are many different aspects that need to be explored. And we have the transceiver designs and also extending the sensing to imaging, which is also a very important topic nowadays. And also potentially we can also borrow the ideas from the wave number domain to facilitate the waveform design, especially when there's multiple antennas in transmission. Okay, finally, I'm going to give some of the reference for today's talk. I'm sorry that I'm not able to convey so much information within such a short time, but I hope these references can be helpful if you are interested in this direction. And also there are some works, very good works from Professor Fan Liu and very good works from Professor Lei Liu. They are very important for understanding the waveforms. And finally, I want to give a big acknowledgement to my collaborators. They are Weijie Yuan, Zhiqiang Wei, Fan Liu, Burak, Jin Hong, Baoming, and Giuseppe. Thank you very much for the listening.
Thank you, Shuangyang, for your comprehensive and very excellent talk. And this is the following is the Q&A part.
Sure.
I will choose several interesting questions from the audience, maybe 3. Yeah. Mm-hmm. First, let's start from some easy one. Okay.
Okay.
Okay. First is the classical single carrier waveform are well known for their low PAPR.
Right.
As we evolve from classical single carrier to the new waveform like OTFS and AFDM, can these emerging waveforms still maintain these low PAPR advantages?
Well, that's actually a good question, and it's very relevant. Let me see if I can find a picture showing something like this. Yeah, right. So basically, I want to say that OTFS particularly is it's a combination on multi-carrier transmission and a single carrier. That means you are able to have a low PAPR by adjusting the values of M and N. That means if you're in this particular case, if you have a larger M and a smaller N, meaning that you have a smaller time slots, therefore you are degrading entirely from OTFS to a single carrier transmission. And in this case, you can have a very good PAPR, as good as what a single carrier can give you. But however, you are sacrificing by the fact that you are no longer spreading your symbols in the time domain. So there is a trade-off. And of course, it can be done, but you need also some good designs and good compatibility with the channel.
Do you mean OTFS stands between single carrier and OFDM, and it can be flexibly adjusted, right?
Yes. Yes. Thank you for the good summary. Yes, that's precisely what I want to mention.
And about AFDM, any comments on PAPR?
Well, I think I'm not a very good expert on AFDM, but I think in general it can be done. There are many many methods to mitigate the PAPR for AFDM. For example, this is still a multi-carrier based and transmission, and I'm aware of there's a certain type of such as clipping, or this such as clipping that can still decrease the PAPR here. But I think more or less because it has a similar structure to OFDM, I'm in favor of saying that most of the schemes for OFDM can also be used here more or less to decrease the PAPR.
Okay, thank you. The next questions will go to, okay. Can you go back to the last page you shown? OFD, it's about OTFS FBMC and OTFS OFDM. So comparing these two waveforms, which is better against the channel dynamics in 6G? What do you think?
So you let me just get it correctly. So you are talking about OTFS and OFDM?
No, the audience asks because this page shown that OTFS can be based on different multi-carrier modulation schemes, including both OTFS and FBMC.
Yes.
And you know, FBMC, we put filters more dense compared to OFDM in the frequency domain, and it can accommodate more symbols. So resulting in a higher spectrum efficiency, obviously. But he is asking, in terms of robustness against the Doppler, which is better, do you think?
Well, that's actually a difficult question. I would say the goodness of OTFS comes from a high complexity receiver. That means if you are able to do a very good detection at the receiver side, the post shaping does not, in my opinion, matters too much. But of course, the key thing here is that you want to have a good detection performance with a reasonable complexity. In this case, if you are doing FEMC or a certain type of a filter here, I think it's actually a very good idea. I'm aware of some of the combination on OTFS with FEMC, and it turns out the performance is actually quite good. However, I would like to highlight a fact that for this type of channel, using random multiplexing is a very good opinion. And I want to give a big credit to Professor Lei Liu on his invention on this random multiplexing. It actually can have some performance, capacity achieving performance with a reasonable complexity. Thanks.
Yeah. Also, the third question is also related to these slides. Sure. I think it's the most interesting question.
I hope I can.
For OTFS and AFDM, you said a word, propagation-centric.
Yes.
Right. It's trying to actively align with the channel dynamics.
Yes.
And for random multiplexing, you said it's trying to regularize the channel statistically.
Yes.
It's kind of two philosophies for design waveform.
Yes.
Active alignment versus the statistical regularization.
Yes.
So the audience is asking, which one do you think is most likely to dominate the standard? And how will they complement with each other in different use cases?
Right. That's a very, very good question. That's actually a question that I keep asking myself. In my opinion, there is no. I think we need to have a common ground that there is no one for all waveform. So there is no optimal waveform that beats every other waveforms. I would say in most of the cases, propagation-centric, such as OTFS, and channel-agnostic, such as random multiplexing, they have their pros and cons. For example, in random multiplexing, we have a theoretical and provement that is somehow capacity achieving. However, the thing is that it only achieves when you have a very long framework. When you have a very long frame, that means in short frame length, I'm afraid the performance of the random multiplexing is not that good. However, for OTFS, because this two-dimensional spreading can fully exploit the channels, and therefore it has a more or less a very good performance with a reasonably complexity decoder. Therefore, it also has some very good advantages. So, but if you want to mention which one can be the dominant one in the future, I'm not sure. Based on my understanding, I think the key part is the backward compatibility, in the sense that we can see in the 6G discussion, there are many waveforms, candidate waveforms have been proposed, but it turns out that at least as far as what I know, OFDM is still the dominant. That means industry people or most of the industry companies, they do not want to completely change to a new waveform. Therefore, in the standards, I would say a good direction is to have a backward compatibility waveform. As long as we can do a little bit of addition on top of OFDM or single carrier, it will have a big advantage. And this is my personal opinion, of course.
But in terms of backward compatibility,
yes,
it seems like random multiplexing is better.
Why? I'm actually curious. Why?
Because this higher distribution precoder doesn't rely on specific waveform you use, I think, right?
Yes,
it can be used in OFDM, OTFS, AFDM, whether, I think.
But the key problem is that you need to have a random precoder that go across different subcarriers. That means you need to do a joint equalization on different subcarriers. And this is something may not be affordable in practice. However, I'm aware of also a very good work from Lei and Yu Hao on the so-called interleaved frequency division multiplexing, which is a simplified version for random multiplexing by doing some interleaving in the time domain for OFDM. That actually has a very good compatibility with OFDM. And I think in that sense, I would say that it has a good backward compatibility. However, there's still some work to be done in order to reduce the complexity for this joint equalization.
Okay. So also a supplementary questions asked by the audience is how they complement with each other, the two design philosophy.
Yeah, that's something I want to mention. I currently have some ideas, but I can share a little bit, but I don't have a concrete conclusion. I would say that depends on the channel condition. For example, if you are in the CDL model, where you have a cluster of transmissions, what I intend to do is that I would like to use this random multiplexing to deal with the transmissions within each cluster. However, for different clusters, because they are somehow separable, I would still prefer to use a propagation-centric waveform. But this requires a very detailed design and also a good understanding on the channel part, which I have not seen so far. So if there is some good work, please feel free to contact me. I'll be very happy to know how these two things can be combined.
Okay, great. I agree. And as you said, the channel is very difficult. We prefer to use multiplexing, random multiplexing. When channel is a little bit simpler, we prefer to use a propagation-centric waveform, right?
Right.
In terms of ice and in terms of sensing, what do you think?
Great question. That's also something I have been working on, actually. So far, because I'm also a bit new to this direction, so far I did not find a very good way to do estimation. And correct. Actually, this OAMP detection relies heavily on the accuracy on your channel estimation, meaning that if you have a channel state information error, your performance can be degraded. However, I'm also aware of there are some new breakthroughs from Lei's group. He has mentioned to me just yesterday, they are having some new ideas on the channel estimation part, and I'm looking forward to their solutions.
Okay, great. Thank you. This is a very good question, right?
Yes, I like
and there were two more questions comes out. Let me read
Sure.
a little bit and if it is worth to discuss here. Okay, I think I can choose this one. The slides mentions the achievable rates for coherent and non-coherent communication.
Right.
In 6G, extreme high mobility, like low altitude satellite, or hypersonic vehicles. Hypersonic vehicles. Acquiring perfect instantaneous CSI is almost impossible.
True.
Does this imply that the focus of future waveform research will shift to making the non-coherent communication, or so-called blind detection technique, as a core focus of physical layer waveform after years of, once again, after years of silence? Okay, great question. Yeah.
Great question. I like this question because I'm aware of there is a very good non-coherent waveform called MOXIE. Basically, the idea is that it multiplies your symbols on a polynomial, and such that because when you are going through a channel, you are doing a filtering with the channel responses, and sometimes they can be commutative, meaning that you can embed your symbols on the zeros of polynomials. Therefore, you can have a very good performance even you do not know the channel state information. So I think this waveform is actually very powerful for non-coherent communications, and especially when the signal is short. And as far as I know, this has been already quite studied in Germany, because currently I'm from Germany, and there is a good startup and has acquired a lot of funding from this MOXIE idea. So I think if we go back to that question, I think non-coherent communication is indeed a very interesting topic need to be discussed, and it's very difficult. There are some new ideas popping up, which I think is should somehow get attention from the audience.
Sorry, what's the term you mentioned? The MOXIE.
I think it's MOCZ.
MOCZ. Okay.
Yeah, forgive me if I get it wrong, but it's called MOXIE.
Okay, for me it's new. Okay, great.
Yeah.
I think I somehow, to some degree, I agree with the audience questions. I think non-coherent detection might be a good research direction for waveform design in the future, right?
Indeed.
Yeah. Okay. So I think we do not have too much time for the other questions here.
Thank you.
And okay, thanks again for Shuangyang's excellent talk. And I think today's session is that's all, right? Thank the audience for your time and attention, and let's looking forward the next talk, right?
Thank you very much. Okay.
Bye-bye.
Bye-bye.